Heron's formula is used to find the area of a triangle where all that is known are the three sides of the triangle, none of the angles. Now, Heron's formula these days doesn't have any practical applications really, because we can use the law of cosines to find the area of this triangle. So it's not necessary for me to use Heron's formula. It's not necessary for me to know it. It's almost completely useless. Now, why it is in a lot of trigonometry books is because in years past there weren't powerful calculators around. So people couldn't easily calculate the sine, the cosine, or tangent of anything. It was much easier for them to measure, or if they did have a calculator, all they could really do was simple math. I don't even think calculators were commonplace until the 1940s, 50s, and 60s. I believe. It may even be later than that. But even when these calculators were around, they weren't able to calculate the sine, cosine, and tangent of anything. So, Heron's formula has a place back in the olden days where this was more of a problem. But of course now where everyone's programmable calculator can do all kinds of things, it's not a problem at all. And let me show why this is. The formula for the area of a triangle is 1/2 base times height. If I were just to put this on a coordinate plane, I can easily find what the base is of this triangle. Let's see. Now the height would be whatever this is, and that would be A sine B. So I could think of the area as 1/2 A times C times sine B. Now if I have a side-side triangle, then I have A, B, and C. But I don't have this angle B. But I can use the law of cosines to easily find out what that is. And once I know what that is, then I can put sine B of whatever angle that is into my calculator, and I have my height, and then I can finish off whatever this is going to be, depending on the numbers. But like I said, long ago, they couldn't easily do that. If they did have a calculator, it wasn't going to do sine, cosine, and tangent. So they wanted to avoid doing that as much as possible. So that meant having to consult a bunch of tables, and then, of course, they weren't always completely accurate. They were only as accurate as the tables were. Where these calculators are accurate to 10 decimal places or something like that. These tables weren't accurate to 10 decimal places because they didn't have sine of 96.9563 or something like that. They didn't have that. They had to round. So it made the answers less accurate. So why even bother learning Heron's formula? Well, there's not much point in learning Heron's formula. What I'm really going to do is just go over the proof because it's an interesting exercise in trigonometry, and it's probably one of the more, tedious, long proofs, I guess. It's not really even long. It's just if someone's going to be good at this kind of math, they're going to have to learn about proofs and why things are the way they are. If they're going to ever want to apply math to whatever it is, whether it be sciences or just higher math. So it's kind of useful to go through these proofs to see how people built bridges between different parts of math and then put it together and really connected it. So that's why I'm going to go over this. Otherwise I just wouldn't bother. I'd just say go use the law of cosines. So how do I, really what I'm going to be doing in order to get Heron's formula is I need to get a formula that tells me the area of a triangle in nothing but A, B, and C, which are the sides, not the angles. So I need to get rid of this and somehow express this in terms of A, C, and B. And if I look at the law of cosines, I can see it looks very similar to it. 2AC cosine B, but this happens to be a sine. So I need to figure out how to link this B of this formula to the b of this. So if I were to somehow rearrange this to where it would just be b, I would have nothing but a, c, and b. It's nothing but sides of the triangle. And then I could say these things are equal to each other, then I can replace the b with whatever this would be. So that's really what the goal of this formula is. So I need to figure out ways of getting there. And some people can play around with this for a while, and there are going to be different ways of getting there, but this is probably the most simple way. It's just to use the half angle formulas. So sine squared of theta over 2 is equal to 1 minus cosine theta over 2. Cosine squared theta over 2. I'm going to use both of these. 1 plus cosine theta over 2. So both sine squared and cosine squared of theta over 2 are going to give me an answer in the terms of just cosine. So that will be helpful. And then later on I'll show why I use both. So now that I have this, I'm going to rearrange this equation just to be written in terms of cosine b. And then I'll be able to plug this into these formulas over here. So I'll be able to convert this into sine of theta over 2 and this into cosine of theta over 2. So I'm going to take this law of cosines and then just rearrange it into a more convenient form to use in these two formulas. So I'm just going to add this over to the other side and subtract this, so it's just positive. And then divide out. Okay, so I've rearranged this. I have cosine b. So now I can put in cosine b here, and then I'm going to have a way of expressing this in terms of this whole law of sines in terms of sine squared over theta over 2. And same thing with cosine squared theta over 2. So I'm going to put these into both formulas. And then hopefully I'll be able to build a bridge between these two things. That's the whole idea again, it's just to build a bridge between these two formulas. And it just so happens I need to use some other pieces of trigonometry to make it easier. So I'll do cosine squared first. And I'm going to do beta over 2. Or not beta, it almost looked like beta, but b, angle b over 2. And then cosine theta, it's going to be cosine b. So cosine b is equal to all this stuff right here. So I'm just going to put that in. And this is all over 2. Now I'm going to simplify this. So I've got to this point. Now what I want to do is combine these two terms just to write it as one term. So what I'm going to do is multiply top and bottom, or I'm going to put this under one fraction. So to do that, I'm going to multiply this top by 4ac and then make this bottom 4ac. So 1/2 is equal to 2ac over 4ac. So if I were to divide out, I'd get 1/2 again. So I've done that. Now the next step for me is going to be to factor this. And this is able to be factored. It's a squared plus b squared. What's that? Plus c squared as well? Yeah. Well, not squared, but getting ahead of myself. And what would I need to do? Put a minus b and that's it? Yeah. So a squared minus ab, ac, ab, so those cancel out. Minus b squared, positive bc, ac, so that's 2ac, bc, so those cancel out, and c squared. Okay, so that's fine. Over 4ac. Now, in order to simplify things, in Heron's formula, what they say is that they create a new term, and it's really just to make this less messy. They say S is equal to 1/2 A plus B plus C. And it's just to simplify some of the stuff so it's just not a ridiculously massive convoluted formula. So what I'm going to do is start converting as much of this as I can into S's. So this is an easy conversion right here. A plus B plus C, that's 2S. So I'll write that over here, 2S. And then times this. This is a minus B. But this is the same thing as A plus B plus C minus 2B. So it could be S minus, or 2S minus 2B. So times 2S minus 2B. And this is all over 4AC. But I can factor this stuff out, and this can be 4 times S minus B. Factor a 2 out of here. Over 4AC. 4's will cancel out, so this is equal to S times S. Oops. S times S minus B over AC. So that is what cosine squared beta, not beta, B over 2. I've been reading too much chemistry recently. I keep thinking of beta for nuclear reactions, whatever. So now that I've done that one, I need to do the one for sine squared. So let me just circle this one so I don't lose track. I already know what it is. I already remember it, but just so when I look back. Sine squared angle B, not beta, is equal to 1 minus cosine B over 2. So I'm going to make the same substitution from the law of cosines before. Cosine B, I might as well circle this one too. Cosine B is equal to A squared plus C squared minus B squared over 2AC. Make this same substitution in here. So the sine squared is going to be equal to 1 minus A squared C squared minus B squared over, not 4/2AC for now. It will shortly be over 4AC. Over 2. I'll simplify this again the same as last time. 1/2 minus this time. And I do the same thing. I want to get all of these under one fraction. So this will be A squared plus C squared minus B squared. Oh, no. Well, I could write it like that, but then I don't really want to do that. I'm just going to change the signs. So I'll have minus a squared minus c squared plus b squared plus 2ac over 4ac. And again, I need to factor this. So this will be a, what do I have, positive b. So I'll need 2 minus b's then. And then in order for these to be positive, I need the positive a and minus c to be on opposite sides, I think. Minus c. Yes, yes. Okay. So then on this side I'll have minus a. And then I'll also have minus b here. And positive c. So minus a squared minus ab positive ac. Good. And then I had minus ab. So this will be positive ab, so they'll cancel out. Positive b squared minus cb. Another positive ac, so 2ac. Okay, so that's positive cb, so this is going to be minus cb. And then minus c squared. Okay, so excellent. So this works out. 4ac. Same thing as last time. S is equal to 1/2 a plus b plus c. So I'm going to convert this into s's as much as I can. So I can say that this is a plus b plus c. And what's minus here? Is there a better way to write this? Actually, I can just make these positives, can't I? Positive AB. Positive AB. Minus AB. Positive CB. Or minus CB. Yeah, this will be easier. Okay, yeah. Yeah, I think I messed that up. But that's fine. And then this will be minus 2c. So this is the same thing as that. And then this is the same. No, I'm going to put it over here. This is the same as a plus b plus c. And then the a here is minus, so minus 2a. So I can write this as 2s minus 2c. And then 2s minus 2a. And then in both cases I can factor out at 2. So this is 4 times s minus c, s minus a, 4ac is equal to just s minus c, s minus a. So that's that one. So now I almost can finish this formula. So let me rewrite everything down here because this is getting a little bit too ridiculous. So 1/2 to area. So I'm trying to get the area. Area is equal to 1/2 AC sine of B. So right now I have these two things. I have sine squared of, not theta, b over 2 is equal to, may as well put these in alphabetical order this time, s minus c over ac, and then I have cosine squared b over 2 is equal to s times s minus b over ac. Now I'm very close to being able to just inserting this into here, but this is b, and this is b over 2, and I can't just say, well, b over 2, because then it would just change the entire everything back here, and I have to recalculate it, and then I'd have something different. So that doesn't work. So I need to figure out a way of just writing this as b over 2, and then being able to substitute in, because I can take the square root and then I'm just left with sine b over 2. So ultimately, so let me just write that now. So let's take the square root of both sides, and then there's no sine squared or cosine squared. And there's plus or minus, but who cares about that? So I need to figure out a way of writing this as sine of b over 2. And one way I can do that is by writing sine b as sine of 2 times b over 2. And what I can now use is the double angle formula. Sine of 2 theta is equal to 2 sine theta cosine theta, I think. I think this is what it is. If it's wrong, I'll know it, but let me just do it. To 2 sine theta cosine theta, so I'm just going to substitute this in here, because sine b is equal to whatever this, 2 sine b over 2, so it's the same thing as this, where theta in this case is b over 2. Sine 2b over 2 is equal to 2 sine b over 2 cosine b over 2. That's the point. So now it's obvious why I did both of them, as opposed to just one of them. But if I hadn't known that, I could have just done the sine one, and then I'd have gotten to this point and be like, oh yeah, well I need to calculate the cosine one as well. I've just gone back and done that. But I didn't feel like doing that. So I just did it at the beginning. So now I know that the area is equal to 1/2 AC, and now I've replaced sine b with sine 2 times b over 2, which is equal to sine of 2b over 2, which is equal to this. Sine 2 sine b over 2 cosine b over 2, and then this 1/2 and 2 are going to cancel, so I'm left with AC sine b over 2 cosine b over 2. And now I just go back over here and I replace this stuff in here. So I have cosine b over 2. Remember this was cosine squared and this was sine squared, and I just took the square root. So I'm just going to take these and then put them down there. So this is going to be equal to, sorry, I got rid of the 1/2. So it's AC, we'll do sine first. So I'll just put a bracket here so it's not confusing. S minus A, S minus B, no, C, over AC, and then the other one is S times S minus B over AC, square root as well. I'm going to multiply these two things together. So AC, so these are the square roots, so I can just multiply them together just fine. And I'm going to be left with S times S minus A, S minus B, S minus C. And then AC, AC, that's A squared, C squared, all under the square root. Now, since these are squares, I can just take the square root of them and then pull them out of this radical. So the AC and AC are going to cancel each other out. So this is going to be, I'm going to take the square root of these, and then that's going to put AC under here. So these will cancel out. So I'll be left with the area is equal to S minus A, S minus B, S minus C, where S is equal to 1/2 A plus B plus C. And this is Heron's formula. So I have the area of a triangle written in nothing but A, B, and C, where A, B, and C are all the sides. So we did all this work, and it was an interesting application of different things that I would have learned in this course: half angle formula, double angle formula, law of cosines. So it's definitely a good application of some trigonomic functions and formulas. But really we get to something that's just not all that useful. I could have gone all the way back up here and just used this law of cosines, figured out what sine B was, taken whatever that angle was and multiplied it by 1/2 AC, and I would have had the area of the triangle as well. But it's useful to understand how a lot of these formulas are made. There's an idea, there's this formula right here, and if I wanted to express this in nothing but sides of the triangle, I know that there's the law of cosines where I can see that there's a B here, and if I could just write this B in terms of A, C, and B, then I would have a formula for that. But I had to build this whole bridge in order to do that. So it's very useful to see how that's done in math, because that is a lot of what higher math is going to be about, as opposed to the practical merits of Heron's formula these days anyways.